All right, welcome to lesson 9. The objective for today is to continue our conversation about how we can represent our functions using graphs and how we can use that to understand situations. And so, over the past couple of lessons, you've been talking about how to graph functions, how to recognize key parts of functions, and now we're really putting it all together to now compare functions to one another. And so our learning objective for today is I can compare the features of the graph of functions and explain what they mean in the situations represented. And specifically today, we're going to talk about intersections between graphs and what those represent. So let's get right into it. So for our first activity, the graph shows the population of Baltimore and Cleveland in the 20th century. B of T is a population of Baltimore in the year T, and C of T is a population of Cleveland in the year T. So our first responsibility is take a look at what is my input and what is my output. And you could see this by reading the situation, but you could also see it by looking at the graph. I know that my input is an input of time, in this case, T. And the T is not minutes and seconds, it is in years. So we are talking about our input as an input of time in years. On the other hand, our output is represented by our population. Population is our output, and this is represented by the number of people. In this case, our population of Baltimore and our population of Cleveland. And both of these graphs are marked and color coded to display the different types of graph. And so now when we have it all on one single graph, we can describe what is happening and what is the situation as we go along. So we're starting off with a little warm up, right? Estimate B of 1930 and explain what it means in this situation. Remember, the inside here is your input value. Inside here, and I'll match the color. Your inside is your input value. And the entire situation here represents your output. All right, so we're looking at our input of 1930, and we want to see what is my population when B, the population of Baltimore, is at 1930. So you can see that exactly in the graph, and if you need to use a sketch thing to take a look at where it is, then feel free to use that. So nothing new yet. And so then the question becomes, how can I compare my graphs? How can I look at what is going on? And so here are pairs of statements about the two populations in each pair, in each pair, one of these statements is true. And so you want to determine which one is true. So for example, for pair 1, B of 2000 is greater than C of 2000, or B of 2000 is less than C of 2000. So I'm going to go back to my graph. I'm going to see where is B of 2000. So here is my input of 2000. Here's my input value. And I know that Baltimore is in blue. And so Baltimore has a population of a little more than 600,000. On the other hand, Cleveland has a population of a little more than 400,000. And so in this scenario, I know that my population of Baltimore, of 2000, in the year 2000, is greater than my population in Cleveland in the year 2000. And so I know that I know that this scenario is correct. And so do the same for the second one. What is your input value? In 1990, what is happening, right? In 1990, where I have this, and so what does this situation represent? And we want to go a little bit further with that by looking at, okay, where are the two populations the same? And if you look at your graph, right, we're looking at comparing each of my scenarios in my graph. And so at what point is the population the same amount, which means my output value is the exact same. And so you can see that visually in your graph where the graph intersects with each other, because at this point, between 1940 and 1950, right, I would say, let's say it's around 1945, the population of Baltimore, right, my B of 1945 is around, I'm going to just say around 900,000. I also know that at the same time in 1945, my population of Cleveland was also 1900. Sorry, 19,000. 1900,000, excuse me. Right? And so these two populations are the same. And so intersections in the graph represent when my input and my output values are exactly the same. And this is significant in many ways. It can help us find issues of population, distance and time. And so we'll be talking a little bit more of that throughout this lesson. And so that is generally what the first activity is asking you to do. And I want you to do the same for percentage of homes that have a landline and percentage of homes that have only a cell phone. So what is happening here in this scenario? And what does that represent? And so that's the key part of today. And so determine whether these situations are true or not, which this should look familiar from one of our previous lessons when we're comparing function notation. And you want to talk about what is happening when the percentage of cell phones is increasing and how the other one is increasing as well. This question, you should look back to lesson 7. Lesson 7 goes into rate of change, if that looks familiar, right? Look for what happens between 2004 and 2015. And if you need to choose both of those points to determine your rate of change, that is what you should be doing. And so last but not least, you have lesson 9.3. In 9.3, you want to match your graphs to scenarios, right? You aren't creating any graph. You are going to be matching your graph to scenarios. There's 4 scenarios and 3 different graphs. So choose your 3 scenarios that correctly describe the 3 graphs. And when you determine which one does not have a pair, I want you to sketch that graph for me. And you can use this. You can use A, B, and C over here to help you determine the answer. Right? If you need to see it bigger, make sure you can just click on it once, and it will help you see what's happening when B and C equals 4, right? What is the value and how do they compare with each other? And last but not least, we have activity 4. In this case, we are taking a little bit outside of our situation, just determining what is happening when we have 2 functions and what does that represent. So I want you to go one by one through each scenario and determine what is happening, right? At f of 2, so I'm looking at 2 here, this scenario, right? When my x-axis equals 2, right? My input value, what are my outputs? At f of 2, this is 4. At g of 2, this is around 7.5. And so I know that this is bigger, so this should be my relationship. And so we're just doing a little more practice pulling together what we've been doing about function notation and how we can see that description in the graph. And so that is the main objective for today. As always, if you're a little confused about anything, the lesson summary is here for you if you have any questions as well. I will see you in lesson 10 and 11.